Greetings and welcome back. So we're in the in the throes of trying to think through this problem of the amphibians on the islands in the Gulf of Guinea in Africa. And as you can see, this is turning into something like a six vignette sort of story. And it's required us to take care of some technical business. So in the previous vignette, we considered the entropy. And now we're going to use that knowledge of the entropy in order to understand osmotic pressure or to understand flow of water across an impermeable membrane, even at the cost of doing work. So the idea is shown here schematically, which I already showed in a cartoon. And by the way, this is a vignette for which I did the analysis ahead of time, and I'm going to walk you through it. And my reasoning is that I didn't want to make an error as I was going along, and I'm hopeful that I didn't in this case. So the picture here is that I start out with this initial configuration, and this is lots of times the way that I think about thermodynamics, which is you have some situation, it's constrained, and the system is stable in this constrained state. And now you remove a constraint and ask what happens to the system in the absence of the constraint. Here, what we do is, as I show you here on the right, we poke some holes in the red barrier, which are small enough to prohibit the green molecules from crossing, but big enough so that water can go across that barrier. And what happens, what we see, is that the level of water on the right over here goes down, and the level of the water over here on the left goes up. That means work has to be done against gravity, but the idea is that the entropic advantage is willing to pay the potential energy cost of lifting the water. So the way that we're going to reason this out is by appealing to the free energy. So as I mentioned in a previous vignette, our goal is to write the free energy as a function of delta H and then evaluate dF by dH equals 0 in order to find the minimizer of the free energy. So in other words, this is a one parameter family. The free energy depends on the single parameter delta H, and what we're interested in finding out is what delta H is optimal in terms of lowering the free energy. So there's two contributions. We need to figure out the before and after of the potential energy. So that means we compare this state over here to this state. And we see that the difference is that over here, this water was lifted relative to its original position, and this water down here was basically carved out and put over on this other side. And so what we need to do is we need to compute the change in gravitational potential energy. So let's start by evaluating the gravitational potential energy of a column of water of height h and of cross-sectional area, as I show you here at the bottom, A. So that's the cross-sectional area on the bottom. So I write this first approximately and conceptually by thinking of the water as consisting of a bunch of layers, which I draw here, each of thickness delta Z. So this layer has a thickness delta Z. And what I do is I evaluate the potential energy of that little band of water, that little thin layer of water. How do I do that? I multiply rho times delta x, delta y, delta z, and that gives me the mass of the water inside of this little layer that I mentioned. So the mass of that layer, so I'll write that, mass equals rho delta x, or maybe I should say it differently. Maybe I say it as rho A and then delta Z, where A is the cross-sectional area. And I then multiply by height times G. Remember that the potential energy of a mass is mgh. And so here, the m is rho A delta Z, the h is Z itself, and the g is the gravitational acceleration. Now, I wrote this originally as a sum, as I show you here, but I can convert that into an integral, as shown in the second line, an integral which is a function of z, where we're interested in evaluating integral of z dz from 0 to h, and the outcome of that is shown here. So we know the mass of this column, sorry, the potential energy of that column. And so now we can do the comparison. We're after a comparison. We want to ask what was the final potential energy, what was the initial potential energy. We take the difference between those two. How do I get initial? I had two columns of height h. You can see here. So, I had this column of height h, and I had this column of height h over here. The reason I'm ignoring all the water below is that it doesn't change. And so I'm going to take that as my zero of potential energy. So these two columns, this one and this one, have a potential energy given by 2 times the 1/2 rho AGH squared. Now the final situation, after there's a relaxation or an equilibration, one of the columns went up to height h plus delta h, the other column went down to height h minus delta h. That means that the energy, the potential energy, is given by the sum of the two columns, which you see here, one of them at height h plus delta h, the other at height h minus delta h. We evaluate that difference, u final minus u initial. I do the algebra here, and the outcome is this very simple expression. So the change in potential energy as a result of this delta H change in the level of the water is given right by rho Ag delta H squared. So that's very cool. Now we need to compute the change in the entropy. So when some of the water goes from the right-hand side to the left side, it dilutes out the green molecules, and we want to evaluate how much the entropy has been increased by virtue of that dilution effect. So how do I compute the entropy? Remember that the entropy, according to the Boltzmann scheme, is the Boltzmann constant times the logarithm of the number of configurations. And here what I've done is I've imagined this column that we talked about a few minutes ago. I've imagined this column, terrible drawing, I need to redo it. But maybe I'll just do it in 2D. So I imagine this column and I discretize it. Maybe I'll use black to show that I have this lattice. And each of these little lattice sites is of volume little v. So that volume is little v, one of these little boxes. And the total volume is v left. So the number of little boxes is v left divided by v. The number of lattice sites. And so what I'm saying is basically that the entropy is given by the number of lattice sites, and then I'm imagining. So let me try and say it this way. I'll go down here and do a little bit of an excursion. So the entropy of n molecules in a box with omega lattice sites is equal to kb log of w, which is kb log of omega factorial over omega minus n factorial, which is approximately equal to kb, and I actually should have an n factorial here also, because those particles are indistinguishable. This I can replace as log of omega to the n power over n factorial. So that's the entropy. Note, I was a little bit sloppy above, or not sloppy, but I eliminated a constant. I can always rewrite this as kb log omega to the n minus kb log of n factorial. But this kb log n factorial term is common in both the initial and final states because n doesn't change. The only thing that changes is omega, the size of the box. So at any rate, what you can see here is that I've thrown out the n factorial term, and what's given here is exactly what I just worked out, which is kb log and then the number of lattice sites, which is the total volume divided by the volume of one little box, and then raised to the n power. What about in the final state? In this case, the final entropy is kb log, and then v left, which is this thing, plus a delta h. What do I mean by that? I mean that the amount of volume available in the left side has gone up because the water column has gotten taller by an amount delta H. So in this case, what I find is that the number of latticytes is the final volume divided by little v, which is the volume per latticyte. And so once again, I use the same scheme. Now I can take the difference. Delta S is S final minus S initial. That's given by KB log. And then I factor out the V left over V. You can see that in this guy. And that gives me this quantity. And then I subtract off from that the S initial, which is KB log V left over little v. And what I'm left with after all of that is this simple expression. So what do I find? I find that the change in entropy is NKB log of 1 plus A delta H, which is the volume change, divided by V tot, or V left. So it's delta V over V. That's the change. So I can rewrite this now, the total free energy. There's two contributions. There's the internal energy piece, and there's the entropy piece. And I note here that I'm going to use log of 1 plus x is approximately equal to x. So that's what I used in this transition between this line and this line. So I have the free energy as a function of my single parameter, delta H. And now what I do is minimize with respect to delta H. I move around in free energy space by sliding delta H, and I ask, where will I get a minimum? So by taking the derivative of this term, I get a 2 rho Ag delta H. By taking the derivative of this term, I get a constant, which is minus NKBT A divided by V left. That's this. Those two things are equal to 0, and that corresponds to the condition that the hydrostatic pressure is equal to the osmotic pressure. This thing pi is what we refer to as the osmotic pressure. So this whole exercise was meant to illustrate to us the importance of entropic driving forces. Entropic driving forces are a big, big player in biology, in cell biology, in molecular biology. There are tons of opportunities for entropy to change, and that entropy change leads to a spontaneous direction to physical processes or chemical processes. And what we saw is that if we open up this membrane, as I showed up in the upper right here, then what will happen is water will flow in order to reduce the free energy or to maximize the entropy, I think is perhaps a more suitable way to say it. So what have we accomplished? This was really intended to convey to you how entropy is related to sticking a frog in salt water. Why? Because there's an osmotic pressure. The osmotic pressure provides a driving force for water flow. What I mean by that is that if I put this semi-permeable membrane, I have the frog, it's got a semi-permeable membrane, I put it in salt water, and what will happen, the way I think of it intuitively, is that the water will leave the frog in order to dilute the ocean. Of course, it's a losing battle, but that's what it's trying to do. It's trying to change the entropy of the ocean by giving more water so that the salt has more places to jiggle around, I think is the way to think about it. So what we'll do in the final vignette on this Sao Tome problem is we will talk about the flux. And what I mean by this, we'll consider our spherical frog, and then we'll ask the question, how long will it take, given this relationship between the flux and the delta C, in order for the water to have all flowed out of the frog? So that's the